Alright, so we're starting chapter 4, and we're going to be talking about radian and degree measures today. But let's first of all talk about standard position. When we're drawing angles on the coordinate plane, we're going to be using standard position. So it's important that you guys know what this is. First of all, the vertex of the angle is at the origin. Okay? It's at the origin. And also, one side of the angle will always be on the positive x-axis. We call that the initial side. Initial is another word for starting. Okay, this is where our angle is going to start. Then you'll see this arrow drawn. It's rotating. Okay? And wherever the angle ends up, we call that side the terminal side. Terminal is another word for end, or ending. The terminal side. That's what it means to be in standard position. Okay? Another aspect of standard position is the fact that the direction your angle rotates does make a difference in the measurement of your angle. You'll notice here, if we're rotating counterclockwise or upward from the positive x-axis, that's a positive angle. Okay? If we're rotating clockwise, we're going to be going down from that positive x-axis. That's going to give us a negative angle. So that's going to be something important to recognize as we move forward as well. Okay. Now you'll see here that obviously we have two distinct angles. We have this angle here, and we have this angle here. You know, one positive and one negative. Okay. However, it is possible to have a positive and a negative angle that actually look like all the same angle. And that's where we get this concept of coterminal angles. All right, coterminal angles. The prefix here, co, means together. Okay, so these are angles whose terminal sides are together. All right, easy way to remember that term, coterminal. These are angles in standard position with the same terminal side, but different measures. Alright, so you see here, they use the Greek letters alpha and beta to represent these two angles. You'll notice they have the initial side here on the positive x-axis, but alpha rotates in the positive direction, and I'm going to say that that's 220 degrees approximately. Okay? Well, beta rotates in the negative direction. Okay? Now, a full circle is how many degrees? 360. Okay? It's 360 degrees. So how many more degrees would we need to make the full 360?
140.
140. Okay? So, when this one's rotating in the positive direction, 220, this one, beta, has to rotate a negative 140 degrees to be coterminal with the 220 degree angle. Mm-hmm.
I don't understand how you know that that's two angles and not just a negative angle.
Well, we know it is because they drew two separate angles.
Oh, okay.
Okay? And you're right, if they didn't draw any of the little arrows, we wouldn't know which one they were talking about, actually. So, the nice thing is, though, that these two angles, while they have different measures, a lot of the trig properties that we'll look at will apply regardless of which measurement you look at. Okay? For instance, if I took the sine of 220 degrees and the sine of negative 140 degrees, I'd actually get the same thing. But we'll get to that. That's later, end of the week, beginning of next week. So, now those aren't the only two angles that share that terminal side. How else do you think I could end up with this terminal side in standard position?
Wait, if it was on the other side?
If I'm in standard position, so I have this side here, and I got this side here, okay? But I want a measurement other than 220 or negative 140.
Couldn't you like flip it?
How do you mean?
Wait, no, it's still the same measurement. Couldn't you move the initial side?
Well, then it wouldn't be in standard position.
But like move it to the other one.
Well, yeah, if you move it anywhere, it's not going to be in standard position anymore. Okay?
Can you go around one more time and add 360 to one and subtract 360 from the other?
Yeah, we could take an extra lap around. Alright? We could go a full circle around and then go 220 degrees. Alright, so what measure would that be?
580.
Yeah, 220 plus another lap, another full circle, 360, would give us 580 degrees. Okay?
Wait, but why are we doing that? I'm confused.
Because we felt like it. I was showing you, there's actually, obviously I could go around twice, right?
Or 3 times.
Or 3 times, or 4 times. There's actually an infinite number of coterminal angles here. Okay? And this is how engineers, when they design things that rotate at all, they're able to figure out, you know, if the arm of our piston or whatever is this long, you know, what's this length? Well, they can do it no matter how many times it's rotated, because those are all coterminal angles. Okay? And that's a very poor example, but it's the best I could come up with off the top of my head. But that anything that rotates, you can figure out, and it's actually what's called periodic behavior that we'll look at later on as we get into the graphs of sine and cosine.
Would B still be what, negative 140?
Yes. Now, we could, if we wanted to, we could rotate around backwards more than once. I could do that. So if I went negative 360 and then negative 140, how many degrees would that be? Yeah, negative 500. So here I actually see there's 4 coterminal angles. 220, negative 140, 580, negative 500. Those are all coterminal angles because they have different measures but the same terminal side. Okay? Now, like I said, you can have an infinite number of these, and that's why you'll see these sometimes shown this way. You'll have that initial 220 degrees, and they'll write it as 220 plus 360n. And they'll just say n is some integer. Okay? If you think about it, n could be the number of extra laps around that you took. So if n was negative, that means you had a lap going backwards. Okay? Or if n is positive, that means you went around the circle in the positive direction and then went the 220. Okay? So if you plug in, 10, that means we went around 10 times and then went 220. So that'd be, 3,600 plus 220, 3,820 degrees. That's a coterminal angle. Okay? Does anyone have any questions about coterminal angles here? Yes.
So when it's asking for a coterminal angle, it's asking for an equation?
Because like, there's.
No, it's asking for a measurement, but this would actually give you,
Because aren't there infinite amount of terminal?
yeah. So they wouldn't say give us the coterminal angle. We would use give us a coterminal angle.
So any answer is acceptable. Like
Yeah.
any two.
Yeah. Any two, and often your book will ask you for a positive and a negative one. So like if you put negative 140 and 580, that would be enough. Comment?
Why is 580 so special?
Well, it's not special, it's just that's another coterminal angle. We could add another 360 degrees and get 940 degrees, and that would be a coterminal angle.
Will it always be represented with the alpha and beta?
No, they just pick.
Okay.
A lot of times, you'll see this throughout the book. If you see a weird symbol you've never seen before, and it's related to an angle, it's probably a Greek letter. Okay? Your book will use Greek letters to represent angles. It's not just your book, but it's used a lot in trigonometry. But if you see a weird symbol, you might see, the alpha, or the beta, or the gamma, not usually a delta, but you might see a theta, or you might even see a phi or c, something like that. You might see those as angles. They're just Greek letters. If you see a weird symbol, chances are it's a Greek letter that they're talking about naming an angle with. Okay.
You know the whole Greek alphabet.
I know most of it. There are a few letters that you don't really use a whole lot, that I sometimes forget, or I forget what order they're in, so. But. Alright, now, what I want to focus the majority of our time on here is how we measure these angles.
Do they always come in pairs? Like would you write in pairs? Or just
What, coterminal angles?
Yeah.
Yeah, you'd have at least two, you'd have at least two, and if you already had one, you might give two others to go with it. Okay. Alright, so degrees. How many degrees are in a circle?
360.
360, okay. So we could define 1 degree as 1/360th of a circle, or of a full rotation, right? So that's what a degree is. That one's kind of obvious, if you think about it. The radian is a little less obvious, okay? A radian is the measure of a central angle. Remember, that's an angle in a circle where its vertex is right on the center of the circle. It's the measure of the central angle that makes the arc length equal to the radius. Alright, now here's a little picture that'll show that. Here's 1 radian, okay? These r's are the radii. And this arc length, for arc length we usually use a lowercase s, okay? That is the same length as the radius, alright? So whatever that central angle is, that's going to be 1 radian, okay? Now the reason why it's related to a circle, and also the reason why we use radians quite a bit, is because the radians often involve pi. Okay, you'll often see radian measurements given in terms of pi. In fact, if you're asked for the exact value of the angle, the exact measurement of the angle in radians, they're asking you to give it in terms of pi. And here's the key conversion factor that you guys need to know. And that is that pi radians equals 180 degrees. Okay, pi radians equals 180 degrees.
You mean pi radian?
Pi radians, 3.14159.
Excuse the interruption. 11th graders who are interested in purchasing and or having a book signed by Jay Asher are welcome to go to the Learning Commons at this time.
Pi is just pi, 3.14159.
So it's not like pi radian, it's just pi.
Well, it is radians. It's a unit of, it's that many radians. Okay, this is 1 radian here. This is 3.14 radians. Okay. Yes.
Can you explain that little circle again? Okay, what's the S?
S is arc length. It's the letter we use for arc length. We're going to talk about arc length more and how to find that specifically later on in the section, but
Why is there a line in the triangle inside the circle?
that's the number 1.
Oh.
That's okay. So. All right, so that's what those are. If you remember this conversion, you can figure out how to convert something from radians to degrees or degrees to radians. There is another unit of measure called the gradient. It's only used in a couple of applications, and I can't for the life of me remember which ones they are now. I've never actually used them, but there are a couple of things in the world that they're used for. Basically, it's just instead of dividing the circle into 360 degrees, they divide it into 300 degrees. So that's that. We're not going to use it at all, but when you look at your calculators, this is going to be one thing that's very important as we get into the trig, is to make sure that if you're using sine, cosine, tangent, any of those, make sure that your calculator's in the proper mode. And you'll see degree, radian, and gradient. Okay? You never want it in gradients. You want it either in degrees or radians, depending on the problem that you're dealing with. Okay? So. Now, like I said, you can convert if you know this, but there is a thing your book gives you that could be helpful if you want to remember it this way. If you're converting from degrees to radians, you're going to multiply your degrees by pi radians over 180 degrees. Okay. If you're converting the other way, from radians to degrees, you're going to multiply the radians by 180 degrees over pi radians.
But isn't pi radians 180 degrees? Or would it be like 180 times the radians?
No, what you just said is correct. Pi radians is 100 degrees. That's a conversion factor. Where it's like if we were trying to convert from pounds to kilograms. We would say 2.2 kilograms equals 1 pound, or is it the other way around? No, 2.2 pounds is approximately 1 kilogram. So if we were converting, we would use those in a ratio. Okay? So, yes?
Wait, so do we multiply, when it says pi radians, do we multiply pi times radians? Or is that just pi?
No, RAD is just a unit of measure.
Oh,
Okay? So, yes?
Can we cross pi and 180 degrees since pi equals 180 degrees? Can we cross?
You don't want to cross those out because that's the conversion. Okay? Let's do an example or two, and I think this will make better sense. If I wanted to convert 36 degrees to radians, okay, I would take the number of degrees, 36, and since I want to convert to radians, I want the radians to be in the numerator of my fraction. I'm going to multiply by a fraction. So the conversion is pi radians is equal to 180 degrees. I put the degrees in the denominator because, look, I want my degrees to cancel out. See that? That's the easiest way to remember it. You want what you're trying to convert to in the numerator. You want what you're converting from in the denominator, so that those will cancel out. So now what you're left with is 36 pi over 180. And then, when you're converting to radians, always give your answer in terms of pi. Alright, so we're simply going to reduce 36 over 180. That's 1/5, so we would do pi over 5 radians. Okay?
Does that equal 36 degrees?
Yes, this is an equivalent measurement. If you put those, yeah, it's the same thing, just a different unit of measure. It's like converting inches to centimeters or, pounds to kilograms. If we're going the other way, what would I multiply 12.56 radians by?
180
Good. 180 would be in the numerator. 2 pi, or not 2 pi, sorry. Pi radians would be in the denominator. I'm multiplying the 12.56 radians by that. Alright, and the whole point of doing that is so that my radians will cancel out. Okay. Now, when you're converting to decimals, you can go ahead, or to degrees, sorry, you can go ahead and put it as a decimal. Use the pi button to make sure it's exact. But we now have 12.56 times 180 over pi, and that gives us 719.6 degrees.
Where's the pi?
Where's what?
Where's the pi?
The pi is right here. I went ahead and actually divided by the value of pi rather than leaving it in terms of pi, because we're getting it in degrees. Okay? So when you're dealing with radians, leave the pi in there. When your answer is in degrees, go ahead and get a decimal answer. Okay? Yes, Tristan.
Wait, so for the graphing calculator, for the sine, cosine, tangent, did you want it in degrees or radians?
It depends on the problem you're working on. You've got to look at the problems that you're dealing with. When you're doing this, it doesn't matter, because 180 is just 180 and pi is just pi. But once we get to the trig, then you've got to look at the problem you're dealing with and make sure you're in the proper mode. Okay. All right. Any other questions? All right, we're going to come back and talk about arc length a little bit more. But before we do, I want to actually look at or mention something in real life that uses angles, and they're in degrees, but we don't have decimal parts of our angles. It's something that I'm sure all of you have seen at least before. Can anyone think of something? It uses degrees. Particularly when you're traveling, you might see these.
Airplanes.
Okay.
It uses degrees.
What uses degrees, but it doesn't have decimal points after the degrees. It has something else.
Temperature.
What?
Thermometer.
Thermometers? No, we're still talking about angles.
Wait, it doesn't have.
The grade of a road.
Okay. But that could still be decimals. Think about locations.
Oh, latitude and
Altitude?
longitude.
Not altitude. There we go. Latitude and longitude. Okay.
Let's try.
Have you guys seen latitude and longitude? It'll be like 53 degrees and so many. You know what comes after?
Minutes.
Minutes and seconds. Yeah, minutes and seconds. Okay. Degrees, minutes, and seconds. Minutes and seconds are a way of showing the decimal part. Okay. and it's an old way, it's a very old way of showing angles, but it actually is still used a lot today. If you ever do anything related to navigation, or if you ever get into the military and you have to use maps a lot, you're going to be using latitude and longitude. If you're an engineer or whatever, you'll have to use latitude and longitude and working with the maps and things. And this is what you will see as an angle. Okay? Now, making sense of that actually is not too hard though. If you keep in mind how normal minutes and seconds work, and instead of hours we have degrees. Okay? So let's think this through, because it's somewhat intuitive if you keep that in mind. If I have 38 degrees and I want to convert from DMS, that's degrees, minutes, and seconds, to degrees with decimals. Okay, you'll see these abbreviations on your calculator, you might see them, or you might see them if you're looking up this topic anywhere. You'll see those abbreviations, DMS and DD.
What's DD again?
Degrees with decimals. So if I'm converting this to degrees with decimals, I know my final answer is going to be 38 point something degrees.
425.
Okay? Well, we can't just do 0.425. Okay? And think about it logically too here. 42 minutes is a little over 2/3 of an hour, right?
70%.
So I know it's going to be over 0.67, right? And does that make sense to you guys?
Yes.
Okay, so it's really tempting just to write down the numbers you see, but you have to actually do the conversion. So let's think about this. We have 38 degrees. If I were converting seconds to minutes, how would I convert 50 seconds to minutes?
So you divide by 60.
It's 1 minute for every 60 seconds. So yeah, we'd put that 50 over 60. So it'd be 42 and 50 60ths
Which is 5.
minutes, which is 5/6. Good. Okay? Now, this obviously is not hours, they're degrees, but it acts the same way. How would we convert minutes to degrees?
2 over 360, right?
Well, not 360,
360.
just over
180.
60.
60. Okay, there's 60 minutes in 1 hour, so there's 60 minutes in 1 degree. Okay, so this would be 38, and you'd put that 42 and 5/6 over 60,
Divide over 60.
because there's 60 minutes in 1 hour, so there's 60 minutes in 1 degree as well. So now we figured that out, and doing that with our calculator isn't too hard. Just figure out the 5/6 first of all, and then add on the 42. Okay, so there's 42.8333 minutes. Okay, now I need to convert that to degrees, so I divide by 60 again, and I get a 0.713888, and so on. Okay, so I have 38.713, and then the 8's repeat, so I'll put that as a 9. Now, when rounding this, do not round this to 38.7. Okay? This is a very precise measurement. Okay, we're down to 50 seconds. Alright? So we ought to give this with a little more precision as well. Alright? We figured it out earlier. 1 minute is approximately like 1.14 miles. Okay, so if I'm just rounding to the nearest minute, or the nearest 10th or 100th of a degree, You know, if my GPS does that, how useful is it if it just gets me within a mile of where I want to go? Okay, not really useful unless I'm looking for a very large field. Okay, so we need more precision. And if you actually look at your GPS, or if you go on Google Maps and click on a spot, you can see the latitude and longitude, and it'll actually give it to, you know, seconds with a number of decimal places after it. Okay, so it's kind of interesting. So let's think through this way. If we're converting from degrees of decimals to degrees, minutes, and seconds,
16 degrees,
good. 16 degrees.
and you multiply 8.811 times 60.
Very good. Okay. Multiply the 0.811 times 60. Okay. And you get, is it 48.66?
Yes.
All right. Okay. So we get 48.66. Now, what does that tell us?
48 minutes.
48 minutes. Okay. We got to take the 48, and that's how many minutes we have.
Isn't it 49? Because 66.
Yeah, it should be.
Well, what do I have to do with the 0.66?
You have to make it into
Seconds.
seconds.
Take it to a second.
That's going to tell us how many seconds there are. So 0.66 times 60 gives us what?
39. No.
Was it 39.6?
39.6.
Now, here we can go ahead and round to the nearest second. So it would be 40 seconds. Okay? So 16.1 or 0.811 degrees is 16 degrees, 48 minutes, 40 seconds. So, are there any questions on the conversion here? You keep in mind, you know, minutes, seconds, hours, or degrees. It's actually not something you haven't done before, it's just in a different context here.
Would we round 48.6 to 49?
No, because you're using that 0.66 down here.
So we only round the seconds?
You only round the seconds, yeah. Because this is 48 minutes and then a partial minute. So you're figuring out how much of that minute you've got. If you think about it too, 0.66 is about 2/3, right? 2/3 of a minute is 40 seconds. You know, so you can kind of see it there. If you had a 0.5, you know there's 30 minutes in an hour, so you could just make it 30 minutes. You wouldn't even have to do the math to convert it, if you keep in mind that. So, now like I said, this is often used in latitude and longitude. All right, I'll just kind of review this real briefly to show you how this works, okay? Latitude goes side to side. The equator is 0 degrees latitude. If you think your the muscles on the sides of your rib cage are your lats, okay? Or lateral movement is from side to side, right? So latitude are the lines that go side to side on the equator. They're a little trickier to work with because as you go north or south, those circles get smaller in circumference, okay? But they're measured actually from the center of the earth as an angle up or down from your equator. So if I measured 30 degrees up from the equator, that's 30 degrees north latitude, okay?
Even if it was pointing the other way, it would still. Like if you had
Oh.
to look at it.
You mean if it were like this?
Yeah.
Yes.
that's what
this, any point along this, around the globe there, would be 30 degrees north latitude.
We wouldn't say that's northeast.
No, because the east and west is our longitude.
Oh,
Okay? Now, the 0 degrees longitude, actually, that's known as the prime meridian, or just 0 degrees longitude. It goes through Greenwich, England. I'll put prime meridian here too.
You know why they chose Greenwich, England? Just curious.
That's the same thing.
I'm not totally sure.
Because it's a center of the.
I think it's because that's where people who were setting this up originally were, or something like that. I don't remember the history behind it. But anyways, this is a little easier to work with because every longitudinal line goes through the north and south poles, so they're all the same circumference. And what we do is we measure an angle to the east or the west of this 0 degrees. Okay, so if I measured 30 degrees to the right, that'd be 30 degrees east, and this circle here would be 30 degrees east longitude. Actually, that's the circle that would be formed, but this part right here would be 30 degrees east. Yes?
It was like 180 longitude, right? 90 in the east and 90 in the west side. Total
Well, it could go up to 180 degrees.
Yeah.
Yeah, 180 degrees longitude would actually be that dotted line that I had drawn here. That'd be the 180 degrees. Cause
There's
it's,
90 in the east and 90 in the west.
yeah, 90 would be going, halfway. So. Okay. So that's how those work. You will run into some things dealing with latitude and longitude. Locations on the globe and really distances on the globe are, we need latitude and longitudinal measurements in order to find distances on the globe, because it really gets into what's known as spherical geometry, which is geometry on a sphere, which our Earth is. But there's also trig involved and things like that. And if we use the angles of latitude and longitude, we can then use things like the Pythagorean theorem to figure out distances. Okay, it's also why, a lot of you have traveled a lot more than I have, but if you were going from, depending on what part of the country you're in, if you're going to Europe or something, they might take you over the North Pole. Or something like that, depending on where on the Earth you were going. Part of that also has to do with jet streams and those kinds of things, but it's kind of interesting. If you look at the path, next time you fly, look at the path that your flight's going to take and see if it's what you anticipated it taking. Okay. So where we're going to start tomorrow is we're going to start looking at arc length, okay? Arc length is a portion of the circumference, and it's really determined by a central angle. It's that central angle, if you remember, is an angle in a circle where the vertex is the center of the circle, and it's formed by 2 radii. But I mentioned this earlier, arc length is a lowercase s, and we'll be looking at that more closely tomorrow, okay? Now, we don't have time to get into it too much here, but there are some problems related to, in the homework here, there are some problems related to arc length. Obviously, you could skip those for right now. If you want to work ahead a little bit and try those, you can. Okay?